We are continuing with continuity of functions, and we looked at that polynomials, those are continuous everywhere. Just recall to show that something is continuous at a value x equals c, we have to show that the limit exists at x equals c, meaning that the left and the right hand limit are the same. F of c exists, and the limit as x approaches c of f of x equals f of c. So we were just looking at just a single equation and seeing about limits and where it was continuous. Let's now look at piecewise functions. So piecewise functions are functions that have multiple equations, and depending on what your input is, your x value depends on what equation that you're going to use. And so let's look at, well, we might as well just start with, let's start with 20. So looking at number 20. So when you're graphing a piecewise function, I tend to graph each piece separately, but I'm very careful with how far I extend my graph, and I make sure I don't extend it past the values on my inequality. The other thing that's really important to do is we always want to see what's going on the end values of those inequality. And we want to plug those in for that equation, even if it's not included. And if it's not included, maybe putting a little note saying that you need to open a circle there. So we have f of x, and we're just going to rewrite it so I can scroll up, is equal to x minus 1 if x is strictly less than 1. Okay, so maybe let's just concentrate on that piece right now. So I know that's a linear equation. I know that's y equals mx plus b, so I could graph it that way. Or we could just plot points. So if I plugged in, and again, I want to see what's always happening at my end value of the inequality, 1, which it isn't included there. But if I plugged it in, 1 minus 1 is 0. And I'm going to put a little note to myself, this is an open circle. And so now we're going to plug in values that are strictly less than 1. Okay, so 0 is less 1. If we plug it into that equation, we get 0 minus 1, which is negative 1. If we plug in negative 1, we get negative 1 minus 1, which is negative 2. So I believe that I have enough information right there so I know what the graph looks like. Okay, so at 1, I had a value of y is 0, but that was an open circle. At 0, I had a y value at negative 1, and at negative 1, I had negative 2. So this is just a line, and it's going to continue as x goes to negative infinity. It's going to continue downwards. So again, make sure that you don't extend this graph to the right of 1 because it's not defined there. And so now let's look at the second equation. And the second equation in this case is just 0. And we're going to use just 0 when x is between 1 and 4. So 0 if 1 is less than or equal to x is less than or equal to 4. Well, basically, this is just a horizontal line. If you have a function equal a constant, that's a horizontal line through that constant. We want to see what's happening at our end values. And so at 1, we get 0. And this is a closed circle because of the equal to part here. And then, again, I said it was a horizontal line, so let's just see what's happening at 4. 4 has the equal to part too, so that's closed. Okay, so let's graph the equation y equals 0 between x equals 1 and 4. So y equals 0, that's basically the x-axis. And we only want it between 1 and 4. We have a horizontal line, solid points at the endpoints of those inequalities. And then the last equation, that last equation was x minus 2. And this was for values if x was strictly greater than 4. So again, I know this is a linear line. My slope is 1. My y-intercept would be -2, although I'm not even going to the y-axis. Let's look at what's happening at the end value of our inequality. So at 4. So plugging in 4 in for x, I get 4 minus 2, which is 2. This is going to be an open circle. And then any number bigger than 4, I can plug in. So 5, I would get 5 minus 2 is 3. Again, I know it's a line, so it'd be extending up this way. Okay, so we graphed our piecewise function. Again, we graphed each equation separately and just made sure that we were limiting to the domain of the values in that inequality it told us to use. We also had to make sure what we were doing again at the endpoints of those inequalities and making a special note to ourselves, was at a closed or an open circle at that endpoint. So notice that at x equals 1, that was an endpoint at both inequalities. And when we're looking for continuity, these are the particular values that we want to look at, especially when we have linear equations as each of our equations, or polynomials. Polynomials are continuous everywhere. So the only problem that we would have with a piecewise function if each equation was a polynomial is where it was changing values or changing equations. But notice again at x equals 1, I was starting to say, we first had an open circle for the first equation at the point 1, 0, but when we plugged in 1 here for the second equation, we got 0. So this basically fills in that circle here. So that's actually continuous at that value because of that point 0. I'm sorry, 1, 0. So let's go back up and see what they asked us to do. So A, graph the given function, did it. B, find the values of x where the function is discontinuous. And C, find the limit from the left and the right at the value of x found in part B. Okay, so looking at our graph, we can see that it's continuous. Continuous meaning there's no open circles or no jumps in the graph. It's going to be continuous everywhere except at this value when x is 4. Okay, so it's the graph of f of x is discontinuous at x equals 4. So they wanted us to show the limit as x approached that number on the left. So if we're coming into this 4 on the left, we're using the pink graph, and the y value we get closer and closer to as we get to 4 is equal to 0. And then if we look at the limit as x approaches 4 on the right of f of x, so coming in on the right-hand side, I'm coming down on the green graph, and I'm getting closer and closer to, not hitting it, but getting closer and closer to 2. So this is equal to 2. And so since the limits does not exist, we just showed that it was discontinuous there. So limit as x approaches 4 of f of x does not exist. And so therefore, one of our conditions of continuity doesn't hold. So therefore the graph is discontinuous there. Okay, so let you finish writing that if you're still writing. And then let's maybe do one more, at least one more of the piecewise. Okay, so looking at, let's say 25, we're given that h of x, this is equal to the piecewise function of 4x plus 4. This is if x is less than or equal to 0. And then we're given a quadratic equation, x squared minus 4x plus 4 if x is greater than 0. Okay, so we want to graph each piece. And again, make sure you're limiting your domain for each piece. And so looking at the first equation, we're going to see what's happening at the end value of the inequality. So at 0, if I plug it in to y equals 4x plus 4, wherever I saw an x, I get 4 times 0 is 0 plus 4 is 4. And this is a closed circle. And then if I plug in something less than 0, so let's say -1. -1 times 4 is -4, plus 4 is 0. One more, -2. 4 times -2 is -8. -8 plus 4 is -4. Okay, so looking at the second equation, I can tell that that's a quadratic equation. I know that this would be a parabola then. I know that my coefficient in front of the x squared is 1. These are just little tips that I know that helps me. That tells me it's facing upwards. Actually, let's go back and graph this one, other piece. So at x equals 0, we had a y value of 4. And we said it was a solid circle. And then at -1, we had 0. And at -2, we had -4. And we can use any values of x less than or equal to 0. So this would extend down. So now again, looking at the other equation. So we have x, our y value is x squared minus 4x plus 4. So I need to see what's going on at my end value of my inequality, even though it's not included. So plugging in 0 here, I get 0 squared minus 4 times 0, still 0, plus 4 is 4. And this is an open circle. So technically I have an open circle here, but it's already closed from the first equation. So I technically would just keep it closed there. If I plug in 1, well, 1 squared is 1 minus 4 plus 4. So this would give me back 1. If I plug in 2, I get 2 squared minus 4 times 2. I need to do this on the side for a second, plus 4. So this is 4 minus 4 times 2, so minus 8 plus 4. So this is going to give me 0. I'm just curious where it's changing back upwards. And the way I can do that is I know the vertex, there's a vertex formula, is -b over 2a. And then depending on what our function in this case, it's h. Plug that value, find in for x to figure out what the y value is. into h of x. So let's find the vertex. That's a point where it's going to be changing direction. So in our case, we have this equation x squared minus 4x plus 4. So my b value is -4 and my a value is 1. So if I plug it in here, I get negative of -4 all over 2 times a, which was 1. So that's 4 over 2, which is 2. Okay, so this is where it's going to start changing direction at this 2, 0. I also know that it's symmetrical across this line, so I can know I have a point here. So I know what the general shape is. And I know it's continuing as x goes to infinity, so it's going to go upwards forever. So if you look at this, this is continuous everywhere. There's no value that we can, where you have a jump or an open circle in the graph that wasn't filled in. Just trying to move that down some. So for part B, we would just say it's continuous everywhere. It's not it's not discontinuous. And so since it's continuous everywhere, we don't have to look at a left or a right limit. So h of x is continuous everywhere. Okay, so there's different types of continuity. So over here, notice that this first piece that we did, we had a jump. This is kind of a jump discontinuity. That is unremovable. We can have discontinuities that happen because of vertical asymptotes. We can't remove vertical asymptotes. But notice that like this, if this had been strictly less than and strictly greater than 0 in this case, that means we would have had an open circle here at 0, 4. If that was the case, we could define that so that would be, this is called a removable discontinuity. If there's just an open circle, and if you define that point, it would then make it continuous there. So let's look at something else. So the following, we want to find the value of k that makes this function a continuous function. Okay, so that means that we need to figure out what, I know that any constant times x squared is continuous everywhere. I know that x plus some constant, that's continuous everywhere. The only problems that I would have is when I'm changing values, changing equations, and that would be at x equals 2. So that's the only thing that we're worried about, is that those give us back the same numbers so that it's continuous. So if we look at f of 2, so let's say, so for f of x equals k times x squared. If we looked at f of 2, so that says we're going to go in and we're going to plug in 2 wherever we see an x, this would equal k times 2 squared, which is 4k. Oops. I said 2, but then I already squared it. So 2 squared is 4k. So I want to do the same thing for that other equation. So let's say we chose g of x to equal the second piece of the equation, x plus 5. Or not x plus 5, I don't know why I said 5, x plus k. And we want to look at what is g of 2. So plug in 2 wherever you see an x there. And this would equal 2 plus k. So in order for f of x equals kx squared if x is less than or equal to 2, or k plus x plus k if x is greater than 2, to be continuous, at x equals 2, we know that these two equations have to equal each other. This 4k has to equal this 2 plus k. So all we have to do here is then figure out what that value would be for k. So we want to solve for k. Okay, so let's get k by itself. We can do that by subtracting k on both sides. So 4k minus k is 3k is equal to 2. And then divide both sides by 3, we get k is equal to 2/3. So if that's the case, then f of x, our equation would be, let's go back in and plug that in wherever we see a k here. So go back up here, plug in 2/3 for k, and plug in 2/3 for k. So it would be 2/3 times x squared if x was less than or equal to 2. And then it would be x plus 2/3 if x was greater than 2. Okay, so we just made it so that that was continuous everywhere. One more. So maybe 28. So let me just rewrite it down. So 28, this one says h of x, this is equal to the first equation, which is rational, 3x squared plus 2x minus 8. And then that's all over x plus 2. And this is if x does not equal -2. Is there a k in there? Nope. The only k is in the second equation, which is 3x plus k. And this is if x equals -2. Okay, so there was a theorem or a rule that says if you have a rational function and the numerator is a polynomial, which it is, And the denominator is a polynomial, which it's continuous everywhere except for the values which set the denominator equals 0. And the value that sets this denominator equals 0 is at -2, which they excluded. And they said, okay, let's give this a point. And so we need to see what's happening here when x is -2. For both equations. So notice if we plug in -2 into that first equation, I'm just going to go in, I'm going to plug in put parentheses wherever I saw an x. And I'm going to replace it with the -2. So if we had 3, you see x there, square it, plus 2, you see an x there, -8 all over, you see an x plus 2. Well, notice if we plug in -2 here, I see my denominator equals 0. Let's simplify the numerator also. So we have 3 times -2 squared, exponents first. So this is 4 times 3, that's 12. And then 2 times -2 is -4 minus 8. So we actually get 0 over 0, which remember was an indeterminate form. It didn't tell us anything. It also tells me that this could have factored, and I would have had like factors that canceled. So let's go back and let's look at 3x squared plus 2x minus 8 all over x plus 2. And let's factor that. So we can use trial and error and try to figure it out, thinking that it's going to factor. Or I tend to use what is called the AC method. And I'm just going to do that on the side for a moment, and then we'll come back and put in that factored form. Okay, so if I want to factor 3x squared plus 2x minus 8. Because my coefficient in front of the x squared is not 1, I can't just factor and see what multiplies to the constant, add to this middle coefficient. Instead, I have to figure out what is my a value, which is 3 in this case, and multiply it times my c value, which is my constant, which is -8 in this case. And so if I multiply those together, 3 times -8, I get -24. I need to figure out what my middle coefficient is, which is 2. And we're trying to think to ourselves, are there 2 numbers that you can think of that you would have to multiply to give you a -24, but when we add them together would add to a 2. Well, I know that my multiplication, I'm getting a negative number. One has to be positive and one has to be negative. I know when I sum those 2 numbers, I'm getting back a positive. So the larger of the 2 factors that would multiply to give me 24 has to be the positive. I tend to just ignore that for a second and think, okay, 3 times 8. Well, if I sum that anyway, it's not going to give me 2. 6 and 4 though. 6 times 4 is 24. And if I did 6 minus 4, that would be 2. So I found those 2 numbers, and it's 6 and -4. That's where we're going to do a trick, and we're going to rewrite the middle term using those 2 numbers. So a lot of times in mathematics, we rewrite things so they help us, but they're equivalent. So 3x squared, instead of 2x, I'm going to write that as 6x minus 4x. So if I combine those like terms, I get back up what I had before, but I don't want to combine them, and that would just be undoing what I did. So once you found those two numbers, rewrote the middle term with those two numbers, we're going to use the factoring by grouping. That's where you group the first two terms together, you group the last two terms together, and then you factor out what they have in common in the first two terms, and then factor out in common what they have in common in the last two terms. Well, if you look at 3 and 6, the biggest thing they have in common with that is a 3. And an x squared and an x, they each have a single x in common. We can pull one x out. And so if you do that, what you're left with would be a single x plus 2. Well, if you were able to find those two numbers that multiplied and added, then this should be factorable. And when you're pulling out the next greatest common factor in these last two terms, it should give us the same thing in the parentheses. And if not, then you didn't do it right, or you need to pull out a negative. So I noticed pulling out a -4, which they both have in common. That would leave me with x minus 2. I'm sorry, x plus 2. So pull out the parentheses. So if I pull out the parentheses there and there, you're left with the 3x minus 4. Okay, so that was kind of a side note, a real quick review of looking at a problem where a wasn't 1 and factoring a quadratic. Okay, so we just found that by factoring that, we just got that that was x plus 2 all times 3x minus 4. Oops. 3x minus 4. So notice, like we said, there, because when we plugged in our value of the limit that, or what the value of the endpoint of our inequality, we saw we got 0 over 0. So I said, okay, well, that means that that numerator is going to factor. We'll have a common factor, which we do, the x plus 2. So really, this reduced down to 3x minus 4. The thing is that x cannot be -2 for this function because it's undefined there. But we want to know what we would get if we reduced it with, we plugged in -2. Okay, so maybe if we let f of x equals 3x minus 4, and we plug in a -2 wherever we see an x, we have f of -2 is equal to 3 times -2 minus 4. So -6 minus 4 is -10. So right now we have an open circle. At the point -2, -10. So we can close that and make it a closed circle if we can figure out what this k has to be up here to make this whole equation 3x plus k equal to our y value, -10. So we need to find when the second piece, 3x plus k equals -2. x is -2. So 3 times -2 plus k has to equal -10. So if we apply that in there, we get -6 plus k equals -10. So add 6 to both sides, -10 plus 6, that's -4. So in order to make that a removable whole, we can let k equal -4. So if you have h of x is equal to, so our top function, that was that 3x squared minus 2x minus 8. All over x plus 2, if x doesn't equal -2. And then here, we're going to plug that in for k here. So this is 3x plus k, but k is -4, so 3x minus 4 if x equals 2. -2. Okay, so we found our k value that would make that piecewise function continuous everywhere. So let me just check on you guys. Okay, so let's look at a limit now where we have the exponential function. And so if we had k of x, and k of x is given to be e, and this is all raised to the square root, and underneath the square root is x minus 1. And so the direction says, find all values x equals a, where the function is discontinuous. Each value of x, give a limit of the function as x approaches a. Be sure to note when the limit doesn't exist. Okay, so first of all, we need to look at the domain. Usually the exponential functions, you have no problems with plugging in values of x, you would get back a real number. The problem here is that our exponent has a radical in it. And so because we have a radical, we have to worry about having negative numbers underneath the square root. Because if we have negative numbers under the square root, then it's not a real number we get back. And so to be in part of the domain, you have to get back a real number if you put it in, a number in. And so we need to figure out, we need x minus 1 has to be greater than or equal to 0. So let's find the domain. And so it's a linear inequality. I can solve this just like I would solve linear equations. I just have to be careful about dividing by negatives or multiplying by negatives. That would change my inequality sign. And so if I add 1 to both sides, I know that x has to be greater than or equal to 1. And so, well, it's discontinuous, or it's not continuous because it's just not defined for any values that are less than or equal to 1. I know that E is continuous everywhere where it's defined. So since E is continuous, since, let's just say y equals E to some function h of x. is continuous for all values. Where x is in the domain. Curious what they wrote. And they didn't. So I guess, and it just wants to know where it's discontinuous. So I guess we could just say, so it's discontinuous. At x less than 1. I also see one in here with a natural log in it. You want to do that too? Okay. So natural logs are just they're inverse functions of our exponential e function. Let's say you're given that f of x is equal to the natural log of the absolute value of x plus 2 in the numerator, all over x minus 3 in the denominator. So we want to find where this is continuous or discontinuous. Well, first of all, we can't have 0 in the denominator. So x cannot be 3. This is undefined. The other thing is we have a log functions, and for logs, when you're taking a log of something, this has to be greater than 0. So for logs and natural logs, what you're taking the log of has to be greater than 0. So we know that x, the absolute value of x plus 2, all over the absolute, all over x minus 3, all of this is within the absolute value, has to be greater than or equal to. No, actually has to be greater than 0. Can't even equal 0. And so we need to figure out what values of x make this greater than 0. When you take an absolute value, what type of number do you get back? So when I take an absolute value of a number, I know I'm going to get back a positive number if I have an absolute value of negative. I know if I take an absolute value of a positive number, it's still positive. Only thing I really have to worry about now is when is my numerator going to be equal to 0? So we can't have, because when my numerator is equal to 0, I get 0 over some number, which is 0, and 0 is not strictly greater than 0. So let's set the numerator equal to 0 and find that. So when is x plus 2 equal to 0? That's when x is negative 2. So we also have to say x cannot be negative 2. So any other number we plug in there, we should be okay. go back to the directions. So find the values x equals a where the function is discontinuous. We found both of them. For each value of x, give the limit of the function as x approaches a. Okay, so I have a natural log, and we have two values we have to look at. So I need to look at the limit as x is approaching 3 from the left and the right. I want to go, let's go look at it. Let's go look at the graph. And I'm going to hope that my computer works when I put back this. So we're going to go to Desmos. Sorry. I don't want to do that. Okay, so we're going to plug in that equation. I'm hoping I know how to write that. ln. I don't think I do. X plus 3. All divided by. Bracket. Divided by x, that should have been x plus 2. X minus 3. Yeah, I didn't like that. I'm not sure how to type that in Desmos. Maybe this is a good time to take a break, and maybe I can figure that out during break. Let's do that. Okay, so I figured out how to graph that on Desmos. And if you look at this, we had saw that there was discontinuous 2 places. At x equals -2, that was the value. It set the denominator equals 0. And it looks like that we have a vertical asymptote there. And then we also have another vertical asymptote at x equals 3, and that's what set the numerator equal to 0. And so what's happening is as x is going to -2, and if we're coming in on the left-hand side of -2, notice that graph shoots downwards. And so we could say that goes to -infinity, but if it goes to an infinity or a -infinity, we also say it doesn't exist. Same thing as we're coming in on the right-hand side. This is going to get closer and closer to the vertical line, x equals -2, but never touch it. And it's shooting down to -infinity. X equals 3, there's a vertical asymptote. The graph is going to be shooting up to +infinity on the left and on the right. Okay. You could also, if you didn't know how to graph it, you could also plug in values. Remember, if you didn't know what was going on with a limit, we could always test by plugging in values. So let me see if I can copy this. So this is something also helpful, and it's probably going to be really helpful in the next section where we have to kind of do a little bit of tedious work at first. Let me see if I can get out of here. So if we go to the scientific calculator and we define our function, so f of x is equal to the absolute value of the x. Is that what it was? Yeah, so x plus 2 all over x minus 3. So if I plug in numbers close to, let's see what's going on at x equals -2. So if I'm coming in on the right, that would be -2.01. So notice that is -6.2. Okay. So let's see if that y value is going there. So let's look at f of -2.00000001. That's even closer to -2. Notice that that value jumps from -6 to -20. So if I add in some more zeros before that 1, notice how that's just continuing to go up. -33 when I add another one, -36, and now it's starting to say undefined because I'm getting so close to 0. I mean, to 2. But you could see that that was growing and it wasn't going towards any one number. And so we could say that's going to -infinity. If I was looking at numbers on the right-hand side of -2 and looking at them coming in to -2 on the right, so what about -1.9? So notice -1.9 is approximately -4. Well, let's add in an extra 9 because that's even closer to -2 on the right. I get a -6.2. Another 9, I get a -8.5. So notice that that also is continuing to, well, actually decrease more and more as I add in more 9s. So -13, -15, -17.7. So I can see that that's not going to one particular value as I approach -2 on the right. And so that's going to -infinity and again doesn't exist. So same sort of idea with the 3. We were looking at what was going on when x equals close to 3. It's undefined at x equals 3 because that's the denominator equals 0. So if I'm coming in on the left, so 2.9 is close to 3 on the left-hand side of 3. That's 3.9 about. 2.99 is getting more closer to 3 on the left, and I get 6. And it's just starting to increase again. So 8.5, 10.8, 13. So it's not getting into one particular value, 15. So same idea, see what's going on as we come in on the right-hand side of 3. So numbers close to 3 on the right-hand side would be like 3.1. I get about 4, 3.01, I get 6, 3.001, 8.5. So again, that's blowing up as we get closer and closer to 3 on the right. And so that there is going to infinity and doesn't exist. So if you're not sure what's going on with a graph, you, like I said, and on homework, you're free to come and use this system to help you. Or if you have a graphing calculator, you can use that too. You won't be able to use those on a test. But I might, if I had something, I probably want to have something where you plug this in. I might already give you a table and say, looking at this table, what's happening as the limit is x is approaching 3. And I might give you values that are coming in on the left and what those y values are. Same thing, giving you x values as it's coming closer to 3 on the right and giving you the y values. And then you understanding by looking at those tables what's going on and telling me what the limit is. Okay. So let's look at a couple applications of continuity, and then we may jump into average rate of change and instantaneous rate of change. So next kind of huge, really a huge topic in calculus, which will be derivatives. Okay, let me pull this up now. Let me make it bigger. Okay, so pulling this from the book. So looking at this, let me just read the problem first, and then we'll look at the graph and we'll try to answer the questions. So the graph shows the profit from the daily production of X thousand kilograms of an industrial chemical. Use the graph to find the following limits. So limit of P of X. P of X is X approaching 6. We're going to look at the limit as X approaches 10 from the left. We're going to look at the limit as X approaches 10 from the right, and the limit as X approaches 10. We're going to answer where is the function discontinuous? What might account for such a discontinuity? And then use the graph to estimate the number of units of the chemical that must be produced before the second shift is as profitable as the first. Okay, so let me just go back and read exactly again what this is saying. The graph shows the profits. We're talking about profit. That's good to know. From the daily production of X thousand kilograms of a chemical. Okay. So profit, this is how much money, and this is the number of units being produced. And now they said, find the limit as X is approaching 6. So first thing you want to do is go to your graph, and let's look at where X equals 6 on that graph. So X equals 6 is here. And so if we come up, we want to see where we're hitting the graph on the y-axis. So let's hit the graph. So it looks like it hits the graph right here. And so it looks like that we have about 500. And then our profit from daily. I just wanted to see if it was in terms of something other. So our profit would be $500. So the limit as X approaches 6 of P of X is equal to $500. Okay, so the next one wanted us to look at the limit as we're coming in on the left-hand side of 10. So limit as X approaches 10 on the left of P of X. So locate 10 on the graph, X equals 10. And then on the left, so we're going to look at the left-hand side. Let's go up to the graph. But the left-hand side is this one here. And so if we're coming in on the left, getting closer and closer to that value of 10, our Y value, or P of X, P of 10 value is looking like it's 1,500. So this is equal to $1,500 of profit. Where the next piece, part C, says let's look at the limit as we're coming in on the right of 10. So if we're coming in on the right of 10, that means we're using this graph on the right. And as we're coming and getting closer and closer to 10 from the right-hand side of the graph, the Y value gets closer and closer to, even though it doesn't include, then it gets closer and closer to 1,000. So then it says find the limit as x approaches 10. And the limit as x approaches 10 of p of x does not exist. And so I might ask you why, or you need to tell me why. And the reason why is that this does not equal this. Well, the limit as x approaches 10 on the left of p of x does not equal the limit as x approaches 10 on the right of p of x. Okay, so looking at this, where is the function discontinuous? Well, we just showed that that the limit as x approaches 10 doesn't exist. And that was one of the conditions that needed to hold in order for it to be continuous. So we can see that it's not continuous at x equals 10. So part E, it's discontinuous at x equals 10. And what might account for that discontinuity? So that is a good question for you to think about for a second. And maybe you can chime in. And I'm going to just pause the recording. Okay, so we're looking at this, and I just kind of asked you guys to think about it a little bit of what might cause that discontinuity at that 10, x equals 10. And so one person chimed in that a change in productivity could happen. And so we talked about what types of things could change that productivity. And someone said, well, maybe they don't work as hard on that second shift. And then I talked about, well, you know, maybe this shift, there's more workers that are coming in, and so that's taking away from their revenue. The company's paying more costs for more workers. Or maybe, you know, this is at 10 hours. Maybe this is an evening shift, a graveyard shift. And to me, I would think that people working in a graveyard shift, or at least I would hope, gets more money as an incentive to take those shifts. Anyway, so those are just a couple things that could happen. I'm sure there's a lot of other great ideas out there that you were thinking about but didn't decide to share with me. Okay, anyways, so the next piece, use the graph to estimate the number of units of a chemical that must be produced before the second shift is as profitable as the first. Okay, so use the graph to estimate the number of units of chemical that must be produced before the second shift is profitable. So looking at this, so that's a jump in the graph here. And so we're trying to figure out when is this second shift going to make $1,500, because that's as profitable as they got. So let's just go make a horizontal line across and see where we hit the graph. And so looking at this, I hit the graph here. And if I come back down, I can see what my value is here. And so the second shift, they need to reach 15 kilograms. So x equals 15, or 15,000 kilograms. Okay, so one more, let's look at one more application problem. Pull it up. Hopefully I can find it. There it is. Actually, let me do this because I want my pen to be bigger. Okay, so cost analysis. So the cost to transport a mobile home depends on the distance, X in miles, that the home is moved. So let C of X represent the cost to move a mobile home X miles. One firm charges as follows. So one firm is going to charge you $4 per mile if you're driving between, well, a little more than 0 miles and equal to 150 miles. They're going to charge you $3 if the distance X is between 150 not including and 400 including, and $2.50 if your value of X is greater than 400. I don't like how that's written. To me, this makes more sense to say X is greater than 400. So we want to find the cost of the mobile home if you're going to drive 130 miles. So C of X, or C of 130, we'll go over here and we want to see which piece does 130 fall in. Well, 130 is less than, right? It's less than 150, so we know they're charging them $4 per mile. And that was 130 miles that they're driving. And so 4 times 130, well, 4 times 0 is 0. 4 times 3 is 12, carry my 1. 4 times 1 is 4, plus 1 is 5. So $520 would be the cost to drive 130 miles. So 150 miles, so looking at C of 150, well, 150 still uses this first equation because this has the equal to part with the 150. And so again, they're just getting charged $4 an hour, not an hour, a mile for 150 miles. And so that gives us $600. So 110, not 110, not 110, 210. So if I look at C of 210, this is equal to, well, 210, we need to figure out, well, X is, 210 is bigger than 150, and 210 falls between 150 and 400. So that tells me I need to use the cost of $3 per mile. So it's going to be 3 times 210. So if we multiply that out, that gives us $630. So you're only paying $30 more than you did at 150, and you're traveling 60 miles more. So D, let's just do that over here. So 400 miles, so C of 400. 400 uses the second equation too because it has the equal to part on the inequality. X is less than or equal to 400. And so $4, not $4, they got a rate, a discount. It's only $3. $3 at 400 miles. So that's $1,200. And then E, we're looking at C of, well, 500. 500 is bigger than 400, and so we're going to charge them $2.50 a mile. So $2.50 all times 500. Okay, let me just do this 5. Where we get? Just do this real quick. 2.5 times 500. So that's 0, 0.
1250.
Thank you. Okay, so $1,250. And then the last question is, where is this discontinuous? Well, the only places where it could be discontinuous, and we have to look at it, is where we're changing inequalities. So it's could occur at 150 miles, and it can occur at 400 miles. And so we want to look at, if I use the equation on the left, the smaller one, less miles, or actually more miles per hour, they're never going to give us the same thing. So it's going to be discontinuous at x equals 150 miles. And it's going to be discontinuous, and let's prove this. At x equals 400 miles. That's when the rate of miles cost per mile is changing. And so we can show that it's discontinuous by showing that the limit doesn't exist. And we can show the limit doesn't exist by the left and the right. So if I look at the limit as x is approaching 150, on the left-hand side of the equation, or left of 150, well, that means I'm looking at a number that is smaller than 150. And that tells me then I would use the cost of $4 per hour. So that would be 4 times x, which we can do direct substitution. And we saw that that was, that's 600. But if we looked at the limit as x is approaching 150 on the right, that means they did more than 150 miles, which means they're getting charged $3 an hour. We're going to do 3 times x. Well, 3 times 150 is 450. So the limit doesn't exist, therefore it's discontinuous. So if I was looking at this and I was running this transport mobile home, and I was really just driving 149 miles, I think I'd drive around the block a couple of times to put it over 150, so I could save about 150 bucks. See where mathematics can save us money? Now, one more time. I'm looking at the limit as x goes to 400. Okay, so 400 on the left, that means that's less than 400 miles, which means I'm going to use that they're charging $3 per mile, and 3 times x, 3 times 400, that's giving us 1,200. But if I look at the limit as x is approaching 400 on the right, that means that I have driven more than 400 miles and I need to use this $2.50 times X, which is 250 times 400. Just 1,000. Yeah, let's just do this. So we got 0, we got 0, we got 20. Hey, okay, I was right. I just want to make sure. So again, you just moved with your family. It was 399 miles. You emptied your U-Haul truck or whatever truck you have, and you tell your wife that you gotta leave. You gotta, or husband, your spouse, I'm leaving you with the kids. I'm gonna go take this truck around 5 or 10 miles, clear my mind and save us 200 bucks. I think maybe they would agree, maybe not. Maybe they say, I'll take it. You stay with the kids, you unpack. Okay, so looking at that, this is a great spot to stop. And we will start with average rate of change and instantaneous rate of change, which will get us into what really a derivative is next week. Let me stop this.